Today what we're going to cover is, let's see, we're going to cover example Python data types. The learning objective today, what you should be able to do after you get out of class, is to understand how Python data types are subtypes of the core Py object. Last time what we covered was the core Py object data structure that underlies everything. Today we'll just do a lightning review of this Py object, just so people remember. So it's the weekend, and then intro to Python sequence types. So tuples, lists, strings. So you'll need this for the assignment. Assignment 2. And then we're just going to go over, the abstract object interface, which is objects abstract.c, and string type, which is object string.c. So we're actually going to, string object.c. We're actually going to spend most of the day on just strings because other objects follow kind of from that. And basically for the assignment, we're going to code annotation assignment 2 released, which will be ints and tuples. That's what you're going to be doing for the assignment. So we're basically going to go over the strings today, and then we're going to go over the ints and tuples for the assignment. So I have the assignment instructions are all on the web page. It's kind of updated in a bit more detail. So just read through the whole assignment page again for the details and indentation. But I mean, pretty much everyone kind of got the point of the assignment, and we went over it orally in class. Okay, so let's get started for today. So today is we're reviewing the Py objects first, and then we're going to go into sequences, and then this abstract object interface, and then just strings as an example of a sequence. Okay, so let's jump right into the review. So let's open up your code editor to Python include, capital I include. And then let's go into object.h. So recall the core Py object is this thing that has, there's all these macros, but really all a Py object is just some empty shell, right? So every object in Python is a Py object, and all it is just a shell with some header in it. And the header has the reference count and the, what else was in the header again? Let me scroll up to make sure I get everything right. So the header has the reference count and the Py object head. Yeah, that's it. And the type, right? So every Py object has a pointer to its type and a pointer to some integer saying how many things are currently pointing to it. And from this, everything else kind of is derived from this Py object. There's another kind of Py object called a Py variable size object, or Py var object, and that's an object that has a variable size. So that also has a size field as well. So for example, a list or a tuple or a string, there's an object and there's some thing in there that's variable size. But for things like an integer, it's just a regular Py object. So Py var object here has a variable sized head. And then there's all these functions that are macros that are convenient, like ref count for getting how many references there are, the type to get the type, size to get the size of a variable sized object. So these are all just convenient things for you. And recall from last time that every object was derived from this core Py object. So everything you do in Python, everything is passing pointers to Py object. That's why when you notice when you're in anything part of the interpreter, there's a bunch of these Py object stars, because basically everything is passing around pointers to these Py objects. So even if you're saying adding two numbers, those numbers are Py integer objects, and they're wrapped in the Py object, and there's some integer part inside. So if you actually look at int object.h, right here, All right, that's the int object. An integer object is simply some pi object, which is the head, and then right after it, there's a long, which is a Python long, a C long integer that represents the value. And you can imagine you go inside and grab this value out and add it and subtract it and so forth. And the key part here is this thing called the structural subtyping, which is it doesn't, C doesn't have inheritance. You can't say in C, you don't say pi_int object, extends whatever pi object. You don't actually say that because in C there's no notion of inheritance. But the way to actually get around this, the trick is that you actually just put the pi object head right in front of it, so that when you have in memory any pi_int object, the first 2 bytes or however many bytes looks just like a pi object. So you can actually use them interchangeably. So notice how pi object head is here, and if we go to object.h, it's just a pi object head, right? So in the same way, every other data structure in Python is a subclass, I guess, of pi object or pi var object, conceptually. Okay, so let's actually pop back now into Python mode. So we just did this lightning review of this pi object. Now let's actually pop back into the Python interpreter, and we're going to introduce these sequences, tuples, lists, and strings. So for those of you who aren't as familiar with Python, don't worry about it because we're just going to introduce them right now. So let's launch just Python on your computer, and that should go into some Python prompt. Should be Python 2 by default on your computer. So Python has this notion of sequence types. So 3 main sequence types in Python are strings, lists, and tuples. So I'll say S is a string, S equals hello, H-E-L-O. And then T is a tuple, T equals parentheses, 1, 2, 3, parentheses, so type that. And then, U is a list, which is the brackets. We can say 4, 5, 6, or something like that. Yeah, so everyone has these typed in. So if you type S, you should get hello. Type T, you should get a parentheses 1, 2, 3, and U, you should get a bracket 4, 5, 6. And if you don't have your Python handy, you can just look along with your partner. Most people are sitting next to their partners, which is good. Can people see in the back? Okay. This? Okay. So for people who are familiar with Python, what's the difference between the T and the U, the tuple and the string type? Tuple and the list types.
Immutability.
Okay, so what does that mean?
You can change the 1, 2, 3 and T.
Right.
So you can assign 3 for the first element of U.
Right. So the difference between a tuple and a list is that a tuple is immutable, which means that you can't actually set an element after you're done with it. So T1 equals 4. It doesn't actually work. So tuple does not support item assignment, and you can't append to it. There's no append method. You basically, once you create a tuple, that tuple is, a tuple is conceptually a tuple is just allocated a fixed size, list of pointers, a fixed size block of pointers, and those things, these pointers, where they point to is just fixed. So a tuple just says, I make a tuple of 3 things. This thing happens to point to an object 1, 2, 3, and that's it. You can't add to it. You can't erase it. That's just it. So in what way can you actually mutate a tuple?
Yeah, if you put a list inside.
Right. So you can actually, the things inside here you can mutate, right? So if the things this is pointing to is mutable, you can actually just go in and change the things inside. But the pointer here hasn't changed, right? So for example, if this thing, like you said, was a list, you can go in and muck around with this list all you want. But the key thing is that this tuple is still immutable because you created it with 3 elements, and each of those pointers, you can't change around those pointers anymore. And because everything's a pi object, right? This tuple is a pi object, this thing is a pi object, this thing is a pi object. Everything is just a pointer to a bunch of things. So all a tuple is conceptually is just an array of pi object pointers, right? It's just a bunch of pi object pointers that each point to things. So as you mentioned, a list is mutable. So a list, you can actually erase this pointer and point to something else. A list, you can actually later on add things, you can remove things. So a tuple is immutable in that you can't modify it after it's created, but you can modify what's inside it. So you can't really guarantee it's totally immutable, right? It's not transitively immutable. Good. And a string is basically a sequence of characters, right? So a string, hello, what is this? S goes to hello. A string conceptually is just a sequence of characters, HELLO or whatever. And it's actually, are strings mutable or not in Python?
Immutable.
Right, they're immutable. So strings are actually immutable in Python. So, so for example, if I say S is hello, I can access like the first element of S, S0, S1, S2, S3. This is just like normal indexing into any sequence. But I can't say that, right? I can't actually set an element to a string. So once a string is made, it's also immutable. So strings and tuples are immutable, which are nice because you can actually use them as keys to dictionaries. Like you can actually, they mean something. They have some kind of identity. Strings are actually better in a way, right? Because a tuple is immutable, but if you have a tuple pointing to mutable things, then, then it contained under your feet. So notice how, so I'm going to clear this, STU. All these things you can use certain operators on. So STU, right? All these things you can use an indexing operator to get to a particular element. For a list, you can actually set it, right? So list U is this, so U0 equals hello if you want. So notice how U of 0 now is pointing to hello. So what we just did, you notice how Python data structures can hold anything, right? So the types aren't set. So U points to a list of 3 things. Initially it points to a list, the first thing's a number 4, second thing's a number 5, third thing's a number 6. And when we did U0 equals hello, all this did is create a hello object. So this is HELLO, this is a string, it's immutable. And it just pointed U0, 0, 0, 1, 2. It just set this pointer from here to here, right? And then notice when it sets the pointer, it increments the reference count for this thing, because one more thing is pointing, it decrements the reference count for this 4. So if hypothetically nothing else is referencing the 4, this thing actually disappears. And now this thing has something held on to it. So all these assignments are just pointer assignments. Nothing is being copied. Well, I guess the pointers are being copied, right? Everything is just a memory address being copied and moved around. And you can do all sorts of things with lists. You can look up the documentation. So these things are all conceptually sequences because they're just a ordered sequence of stuff. So you notice how I have the same syntax for everything. So another thing you can do is you can do a for loop to iterate through a sequence. So you can say for E and S colon, and then enter, and then tab print E. So what this will do is this will iterate through the sequence one element at a time and print it. So what would this print to the screen? You guys can try it.
Hello, 5, 6.
Huh?
No, S.
S is a string. It's a hello string. Well, you can just try it. So this will print out one character on each line. So it prints out one character on each line because when you iterate through a string, you're getting one character at a time through the string. That's just how the iterator works on a string, because a string is a sequence of individual characters. And print puts a new line in. So if I say for E and U, or T, colon print E, I get 1, 2, 3, which is the elements of the tuple, and then for E and U, print E, I get hello 5, 6, because it's whatever the list is. So a for loop basically goes through a sequence in order. That's, there's no magic in there. It's that every sequence defines some kind of iterator that you just iterate right through it. So there are questions about the sequence types at this point, and I went through this super fast on sequences. So in Python, the sequences can hold anything. All you can imagine a sequence is in Python, a sequence is just a bunch of, it's just a block, and each thing is a pointer. The pointer can be whatever. It just actually, the string, the pointers all point to characters, but conceptually they're just pointers to something. And immutable means you can't change the pointers or this thing after it's created. Immutable means you can actually change after it's created. Okay, cool. So with that said, so we went through a lightning review of these sequences. So for the rest of the day, what we're going to be doing is we're actually going to be looking in one kind of sequence in particular, which is a string. So so who knows how strings are implemented in, say, like C? Like what are strings in C? So yeah.
Character array.
Okay, so a character array. Okay, so the most basic thing, so a C string or something, is really just set consecutive bytes in memory, and then it ends with a null byte, right? So this is a ASCII 0, just 1 byte. So 0 0. So just 1 byte. So a C string is really just at the most basic level, this is 1 byte, 1 byte, 1 byte, 1 byte, and then it just ends with a byte that happens to be 0 0 0 0 0 0 0. Like this, every byte is 8 bits, so this is literally just 8 zeros, and this is some number that represents an ASCII character. This is character 124, 118, 200, whatever. I mean, this represents HELL. That's another LO. Right? So in C, a string is just that. It's like, how much space does this C string take? It takes however many bytes it is plus 1. So if your string is 6 long, it actually takes up only 7 bytes of memory. It's actually quite compact. There's all sorts of problems with C strings, right? Because you don't actually know how long it is unless you actually go through the string. You can have all sorts of weird, you can't have a null byte in the string because then it just cuts it off. All sorts of problems in computer security come about because C strings are implemented like this. But this is kind of the most compact way you implement a string. So this is used everywhere. So in Python, a string is actually an object. It's a Py string object that wraps around Py object that has some kind of C string inside of it, conceptually, just like the integers. But it actually has a lot more stuff. So let's actually open up. So we're going to spend the rest of the hour talking about strings as one canonical type. And strings are good to talk about because, one, they're a sequence type, so they're a bit more complicated than an integer. So an integer you'll look at for your assignment, but it's pretty simple. It's like, here's a number inside. There are some more subtleties you'll have to find out, or you have to figure out when you do your assignment. So to get full credit in the assignment, you have to figure out some of the subtleties with integers. But I won't spoil the surprise yet. So let's go include string object.h. So in capital I include. So remember, every H file is just a header file defining the things of the type. There's actually pretty good documentation on it. So let's read this. So type string Py string object represents a character string. An extra 0 byte is reserved at the end to ensure it's 0 terminated, just like a C string. But a size is present, so strings with null bytes in them can be represented. This is an immutable object. So this is exactly what we covered. So it's immutable. Once you create a Py string object, nobody else can modify it. It is 0 terminated, just like a C string, but it actually carries its size with it, which is nice because then you can just find the size instantly. Also, that means that you can also have null bytes in the string. Why would you want to have null bytes in your string, though? Any ideas? Yeah, so you know where it terminates. But then the whole point of this is that you can actually put null bytes in the middle of your string. That's not a terminating null byte. So normally, yeah, the null byte, you have to have a null byte so you know where the string ends. But the point of this is that you actually keep the size. So you can actually imagine your string is so this is the null byte in the end, right? 0 x 0 0. What they said is that this is HAE 0 x 0 0 LLO 1 2 3 4 5 6. So the length is 6. So what this is saying is that it keeps its length of 6. So it knows that actually this thing is 6 long, even though you have a null byte in the middle. Any reasons why people would actually want to do that?
Split it up easily.
Yeah, you can split up easily. I think that in normal, so this string is literally HE0 something, LLO. I think normally you would never want to do that, but when you want to transfer binary data, you might want to. Right? Because if you're using your string to represent a bunch of binary data, like you know, if this string is just actually like a bytecode or something. I don't think there's a 0 bytecode, which is really bad to have that. But imagine you have a bunch of actual binary blobs of data. You might have 0 bytes in the middle somewhere. So you want to use your string to transport it, then you need to support 0 bytes in the middle of your string, because otherwise, if this was a C string, this C string would actually be called HE, and then would be a length 2, which is bad because there's actually a bunch of stuff after it. This is the real end. So by keeping the length, you can support 0 bytes. This is kind of clunky because in Python, it's kind of clunky to use strings to represent binary bytes. So in the new Pythons, you don't have to know this, but in the new Pythons, there's a byte array type or something. There's a special type just for transporting bytes so that you don't actually want to use strings. And in the new Python, strings support what's called Unicode, so for international characters, because this is pretty limiting because it only supports ASCII characters, right? So if you have accents and other things in other languages, you can't really do it in these strings. So the new Python 3, the strings are all, what I said is not true. These strings are completely different because you want to support variable length characters for, you know, international characters. But this is a simple string implementation in Python too, so we'll go with it. There are functions to create new string object, to test an object for stringness to get the string value. No pointer, variant, text size should be applied to hash object, only one string with a given value like this. Built in. So what does this do? Who's familiar with this concept? Nick can explain what that part does. Thoughts? There's some kind of caching thing. Right, so what this kind of does is that it's an optimization, right? It says it actually sped up the interpreter by 20%. So since you guys are interested in optimizations, a lot of the things in the Python interpreter that are optimized are these little tricks that I just put for caching. Because one of the things is a lot of strings are created in Python, because you notice how a lot of things in Python are just strings being passed around. You know, a lot of strings look like Python identifiers, like sys or, you know, or for, or those things. And you know what this caching does is that it just basically creates one copy of certain strings so that you can just have multiple pointers to it. And the reason why this works is because strings are immutable, right? So if I create, I remember this actually didn't work, right? So Java actually does this, but this our hello demo. So if I create, I don't think this actually works in interpreter now, but if I create x equals hello, I'm just using this as a shorthand, but this is really a bunch of characters, right? And then y equals hello. It shouldn't really matter if these two point to different hellos or the x and y point to the exact same hello, right? It shouldn't matter because the hello is immutable. You can't actually mess with it. You can't change it. So by x and y pointing the same one, it's the same thing as them pointing a different one. So as an optimization for certain strings in Python, it actually just creates one copy and has everyone point to that copy. So that just helps speed things up, uses less memory, and is faster. And also equality tests are fast, right? So if you want to compare whether two strings are equal, in the most general case, you need to just go down the two strings to compare whether each character is equal. But if they're just pointing the same thing, you know they're equal. So that's just a fast test. So let's look at the PyString object. Okay, so this is derived from a Py variable size object. So PyString object is the definition. There is a Py object var head. So remember this var head has a reference count, a type, and also a size. So Py object var head represents a variable size object. So it has all three of those. If you look at that macro, I think it expands to these three things. It has a bunch of stuff, these two things which we'll explain, and then this obs val. So what this thing is that it's this weird C syntax, but it basically defines an array, basically. But this thing it says it's of size 1, but you can actually declare this of size anything. Because when you make a PyString object, it'll allocate however much space is needed. So the obs val will stretch to be the size of your string. So I'll show you how this works. So let me see. So let's say I want to create a string of size 3. So the PyString object is actually going to have a bunch of things. It's going to have, this is exactly what it looks like in memory, or sort of. It's going to have a ref count. It has a type pointer. It has a size. It has this OBS hash thing, which we'll talk about, this OBS state thing, which we'll talk about. So all these are fixed size, right? There's a long, an int, a pointer, whatever. These are all fixed size. Now this final thing, OBS val, is pointing down here. It's supposed to only be one big, but when we create an object, we can just call malloc and allocate however big of an object we want. We just allocate enough for, what is it, 3? 3 things, so we need to allocate 4 spots. So this is, you know, what's our size string? This string is called cat, let's say. If it's cat, we'll allocate a thing. This is C, this is A, this is T, this is the 0 byte. That make sense? And our size is actually stored up here because we know it's size 3. I probably didn't get the order right, but you get the point, right? So this is our PyString object. When we allocate it, I'm just guessing, 1, 2, 3, 4, 5, 6, 7, 8, 9. We just do a malloc, you know, we do a malloc allocate 10 bytes, around 10 bytes. Because all these objects are dynamic allocate. You can allocate however many bytes you want. So now if I actually create a string called hello, the PyString object is going to look exactly like this, except it's going to be a lot longer, right? It's going to be a fair amount longer. It has the exact same fields. So there's it. 1, 2, 3, 4, 5. And then this final OBS val thing just happens to be 6 long, right? 1, 2, 3, 4, 5, 6. So it has to be HELLO 0x00, and that's the hello string. So notice how every PyString object could be a different size in memory. This PyString object is of size, I don't know, 10 or whatever. This is of size 15 or whatever. Does that make sense? Because you need to store the whole string inside the string. So the way this is implemented, it's not a pointer somewhere else. So you can imagine another implementation where every PyString object is the same size, and then at the end there's actually a pointer to the outside to somebody else. But in Python, it just is all globbed together in one thing. So that way, if we actually look at it, the PyString type, it's kind of hard to see with the red, but the PyString type is actually not much longer than a CString type. Right? So a C string is this. It's actually just a C string. It's actually pretty efficient. And then we just put on top of it some extra cruft, right? And that extra cruft involves the size, the reference count, and these other things. So the Python string is actually fairly compact. And you can imagine, I mean, you'll do this for assignment, but you can imagine what a tuple or a list looks like. You can imagine it's a similar kind of idea of we have a header that's an object, and we just stuff things inside. So if you notice, if you actually have a PyObject pointer to one of these things, you can only access the first 3 fields, right? Because as far as a PyObject knows, it only knows about these 3 things. And the way to get a PyString pointer to it is that you actually look at the type and you know it's a string, and then you cast it to a string pointer, and then we can get everything. So this is all just kind of playing with C pointers. Okay, so I'm going to erase this super messy drawing. And then we're going to look at what are these 2 things, this S hash, S state thing. Those 2 things are basically what the comments imply. The comments imply that S hash saves recalculation of a hash. S state ensures that only one string with a given value exists. So this is something for so a hash is basically a way of uniquely identifying what an object is. So there's all sorts of hash functions you can use to calculate things for a string. I don't know which one Python uses. It uses some algorithm. Basically, it's just some compact number that's really easy to calculate and to compare for identity. So you don't have to compare the whole string. Let's look in what this S state is. Invariance. Intern dictionary, 2 references. Okay, so there are some invariants in the object. So this is what these things must hold true about this object, right? So this is exactly what it said. OBS val contains OB size plus 1 element. OB size is up here in the head. It's our string is size 5. It contains 6 elements. The last one is 0. It's null terminated. like all C strings are. The hash is the hash of the string, or -1 if we haven't computed the hash yet. So the thing is, once we compute the hash the first time, we just store it in there, so we don't have to compute it again. It's another form of caching. So all these are optimizations. So we don't actually need these two; they're just optimizations. State is not 0 if only the string object is in the intern dictionary. In this case, the two references from intern in this object. So let's look at what intern is. I don't think there's intern. Not intern, mortal. Yeah, so these are all. So interning is the word for caching strings in this case. If you actually look up Java, so Java virtual machine does this, string.intern. So Java does this, Python does this, so this is pretty straightforward. You can just read it on Wikipedia. String intern is a method of storing only one copy of each distinct string, which must be immutable. Makes some things faster. There's a pool. It's basically just caching. It's you can also intern integers. You can just say, I want all the small integers. I want to allocate them ahead of time because I know I'm going to use them a lot. It's just a pure optimization. There's no right. There's no correctness issue. You don't have to use interning if you don't want. It's just fast. So intern is just a word for that. And then all these other helper macros are just for interning. So these are definitions for whether it's intern, this mortal and unmortal, just different kinds of interning, I guess. And then there's all these functions. So pystring check. So this pystring check macros, this checks if you're a string or a subclass of a string. So these are, you're going to see this for every type. So when you see it for integer, basically because Python is dynamically typed, remember every PyObject has a type attached to it. So it needs to conceptually check that type to see if it's the right thing. This is the simplest one. The exact check, it says PyType object. PyType object grabs that type field out of the object. If it equals PyString type, then the address of PyString type, we know it's an exact string. That's why it's called PyString check exact. PyString check will accept a subclass. So if you actually subclass string, because Python you can do object-oriented programming, if you actually create a subclass of string, this PyString check should still pass because you're still a string, even though you're a subclass. But exact means are you exactly the string type? You'll see this a lot in other object codes. This is a pretty standard pattern. And then there's just a lot of functions. There's just a lot of functions to do with strings. We'll go over some of these. Concatenation, attaching strings together, resizing strings equal, checking if they're equal. Intern, these are things for caching. PyString as string, trade safety as speed. I'm just going to go down for all these. I don't think you need to know. These are more advanced objects. Don't worry about these. I'm just flowing through this. I want to see if there's there's a lot of other things. The other macro here that's useful is PyString get size, which we can imagine what it does. It gets how big the string is. And it just calls PySize, which is the macro in the generic object. .h. It just grabs the OB size from the PyVar object. So PySize just grabs how big it is from the variable size object. PyString is string. This actually just grabs the sval out. This grabs the C string out. So this is a useful macro if you're like, I just want to get the string inside of the, I want to get the real C string inside so I can use C functions to operate on it. So remember, OB sval is that thingy in the end. That's a holds an array of characters. That's our string. So that's our way of unboxing the string. And you can imagine integers, floating points, booleans have all these things. Okay, so now let's actually go into string.c, string object.c. So we're in objects, capital O objects. So now we have all the C files. So we had string object.h, so string object.c is in objects, capital O objects. We're going to dive inside. There's going to be a lot of code here, but we won't need to see all of it. So conceptually, if we go to, let me just go to a terminal right here. Open a new one. So, s equals hello. Oh, x equals hello, y equals hello. If I say x equals y, it says true. So what this will do is this will do some kind of equality check to make sure it's true. Let's see if x is y. This actually is intern. So if you notice how this, the is returns the same. So the both actually have the same address. So ID is a way of of finding the memory address of things. So this actually, in this case, it turns out they both, probably because they're small, they both actually were pointing to the same thing. Now, if I create a really big one, I don't know if this will work. Let's see if this works. Let's see if this actually. You said it should paste automatically. It does. Ah, okay, good. So it doesn't actually intern them. It doesn't, but x equals y is true. And so if I do idx, idy, they're different IDs now because they're actually they just allocated 2 big strings. So we actually explore how this works in the code. Now if I say x equals y, now x and y are both pointing to the same thing. So this seems kind of super tricky and confusing, but in reality, you shouldn't be using is for string equality. You should really just use equals because you can't guarantee, Python can't guarantee what it's caching and what it's not. You really should just use equals for every equality because that actually checks the value equality. The way equals is probably implemented, as you can see in the interpreter, is it actually checks whether the pointer is the same. If it's the same, it just says, oh, we're good, we're equal. If it's not the same, then it has to do with slow equality. So let's actually dive into the interpreter for how x equals y works when they're both strings. So type of x is a string, type of y is a string. So, and this will bring us through our abstract thing as well. So let's also open Python ceval, which is our main, ceval.c is our main interpreter. And then let me just write some bytecode just to verify. So this is x equals hello, y equals hello, x equals y. Let's see that. Oops. Yeah, kind of going a bit fast. Compare up. Okay. So what this bytecode says, we're just loading hello next, hello y. This is boring. And then we're going to load both of them and just do a compare op with an equals. So remember the compare op from last time, from last assignment. Let's go into the compare op where the compare op is in ceval and then take the execution from there. So we're assuming x and y are both strings now because they're loaded with strings. So let's go into compare op in the ceval. So if we actually search for compare underscore op, we get right to it. It's really useful to have a text editor where you can search really fast because you can just search. It's line 2275 for if you're looking at the line numbers. It's here 2275, where the first instance is compare op. Okay, so this is where this is what trips some of you up on the assignment, because in the assignment we actually go into this path. Right? In the assignment, the only thing we do is this, because so compare op. You can imagine we're actually popping both of these. We actually didn't pop this, but W and V are the 2 things on top of the stack. In this case, W and V are both string objects. So, W points to some string object, hello. V now points to some string object, hello. I mean, I'm just using a box as this Python string object. Obviously, it has a bunch of other stuff inside, reference counts, blah, 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 but I just represent it. Now, W and V are both pointing to these objects, and we want to do something with it. So, we're going to... It does not pass this check, right? Because this check means, are they both integers? They're not integers. So notice how, for homework 1, if they're both integers, we can go inside here. Else we have to do this slow compare, right? We have to do this slow thing, and then after we do the slow thing, we send the result to x, and then we do something with the x. So let's go inside comp outcome. So some of you actually looked into this for your assignment. So we're going to jump into comp outcome with op arg is equals. It's the what kind of operation we have. We go into here. This is the operation. There's 2 PyObject pointers, W and V, and then we switch based on the operation, right? We're equals, so it's a bunch of different ones. We are here. Okay, so we actually don't match any of these, if you notice, right? Because we don't do exe match, not in, is, not is. Notice how these are really simple, right? So the Python is operator is literally just doing is the 2 pointers equal. The is not operator is doing is the 2 pointers literally not equal. So an is operator in Python, x equals hello, y equals x. X is y is true. That's always going to be true because we're pointing the same thing. So idx, idy. All is doing is just checking the 2 pointers to make sure they're equal. So it's very fast, right? So the code is right here. It's just a pointer check in C. Is not is the opposite. So we can't find it. In is for sequences. Non-in is for sequences. So we can't find it. So let's go all the way down to the rich compare. So this is the most general comparison function because we can't find anywhere else. So where is this? This is in objects, object.c. Because this is notice how this is a generic PyObject method. Because W and V right now are PyObjects. It has no idea they're strings, it has no idea what types they are. This is the thing with Python, right? They have no idea what type anything is right now. So we can't go into string object, we have to just go into object. So let's go into object. PyObject rich compare is here. Can you just do a search? The first PyObject rich compare, 944 in object.c. The arguments switched around a little bit. So V and W are still our two things, right? V is a string, W is a string, op is equals equals. Okay, some stuff. Try to get at you. Let's see. So if the types are equal, and it's not an old style instance. So these two types should be equal because they're both strings, right? So let's see if we can actually jump into here. Fast let's see if we can do rich comp. I think we can actually jump into here because they're not instances. So if we do that, rich compare, TP compare, convert three-way object. Right. So basically this magic in here, we'll go over this detail a little bit. Basically with this magic in here, you'll actually figure this out. I think your assignment might go in here, might not go in here. It's one of these paths. You need to figure out how exactly which path is actually taken for your object. But all the PyObjects implement a bunch of methods. So if we go to objects, string object, .c, if we go down, compare, right here. So what this is, I'm jumping around pretty fast, but what this is it's the Py string type. So every Py string has a bunch of methods it implements. One of these methods is called a TP rich compare method. So it knows, Python knows that every type has some kind of, or most types, has some kind of rich comparison method. And the string one happens to be called string rich compare. If you notice, if you search for TP rich compare, oops, in object.c, TP rich compare is right, it's right here. So macro to get rich. So there's a lot of macros if you see jumping around. So you have to really navigate the code well. It actually grabs the rich compare method out. So this RICH compare macro grabs, where are we? Grabs the PyObject compare, grabs this out. You see that? It grabs it out from the type, and then it calls it on, so this is a function pointer, it calls it on these two things. So this is like kind of a crazy weird level of indirection. Basically what this says is that this grabs V, so we know V and W are the same type now because we're inside here, they're both strings. It grabs the type of V, OB type is just the type. It grabs the rich compare function out of that type, and it puts it in a function pointer here. Now hold this line in your head. It's right here. This string rich compare is the TP rich compare for here. So you imagine for another type, the rich compare is integer rich compare, Boolean, lists, whatever. And this is a pointer to a function. The string rich compare is a function. So it's called a function pointer. And then when you get this function pointer, we dereference it and we call it. So this is calling a function through a function pointer. So if I told you to stare at this code and trace it in a debugger in rich compare, when you get down to here, just by staring at the code, you shouldn't be able to tell me where we jump to next, right? We jump to some function, but I have no idea where it jumps to unless you're actually running, and we know what the type of, we know what V is, we know what VOB type is, we know what FRICH is, and that's the only way we know. We only know at runtime. So this is why this object this function is generic, right? It works with any object. And if it breaks, then we actually give you an error, right? I think FRACH is, so I think if it's null, it actually keeps on going down. Try a three-way comparison. So this is another comparison, but the rich comparison should work. So in our case, if both of them are strings, this will directly jump into the string compare function. So let's go into this string rich compare. So we'll actually call string rich compare. So that's how we jump into here. Notice how now we're in string object.c. We made our way from the interpreter, which is c eval.c, the generic interpreter and handle compare ops. We went to the comp outcome or whatever, because we don't know, it was an integer. And then we jumped into object.c, which is I want to compare objects somehow. And then we ripped out of the type, and then we actually jumped into this. So notice how, as an aside, x equals 1, 2, 3. X is a string, y is an integer. I can do that, right? I can compare that fine. It doesn't break. And it knows that it does a different path, right? Because they're different types now. And it's different types, they're not always not equal, but you can imagine them being equal still, because one could be subtype another one. But it basically calls a more general comparison. So because x and y are the exact same type, we can call this fast comparison. So now we're actually finally in the string. So this is kind of tedious, but we're finally in the string. Now notice how both of these are string objects now, because we know that both of them are strings. So notice from here, v and w are just pi objects. They're generic. We don't know what they are. But because we call the string rich compare, we only call the string rich compare when we both determine that they're strings, and we grab the string rich compare out. We can safely assume these two are strings, because we wouldn't have jumped here if this thing wasn't a string type. And if this thing isn't a string type, we can't call this anyway. So now I guess let's call A and B. These are both strings. And now we actually do the comparison. So notice how we can actually compare with any operation. We can compare with equals, equals, less than, greater than, whatever. So what is less than or greater than for strings? So x equals hello, y equals world. So x is less than y because they're the same length. It's the dictionary sorting order. So I think if we have, let me try this. Oh, it's still true, huh? I thought it did by length as well, but I guess it doesn't. Okay, so this is alphabetical. Okay. You can imagine another sorting that goes by length as well as by, actually, does that work? Okay, so it's still true. So it is alphabetical. So you can imagine passing less than here or greater than, but the point is it gets into the string really indirectly. So now this code is all just pretty straightforward. There's a size of A and B, the minimum length. Make sure both are strings. Okay, good. So this is another paranoid check, just to make sure. It's always good to be paranoid. If they're the same pointer, then if it's equals, less than or equals, I'm assuming this is less than or equals, greater than equals, we return true. Otherwise, return false. This is a fast optimization again. If they're literally pointing the same string, then they are equal to each other, they're less than equal, and they're greater than equal, and so forth. If we're doing EQ, which is what we're doing, then if the two sizes are the same, two things the same, and memcomp true, this is the memory comparison. This is MEMCMP is a C. These are all just native C functions. This is comparing the two arrays on both sides of length size. This is exactly what you'd imagine. This is just an optimization again. Check to see if the first character is the same. If the first character is not the same, we forget it. These are all optimizations, right? That we want to check if they're the size the same first. So let's imagine a pi string object and pi string object. So right, there are two kind of longish things. There are two kind of longish things down here, and you imagine there are two things down here, and all this, remember, above it is all the pi object junk, along with some other junk in the string, and then this is OB sval, right? It starts here, and it has a bunch of slots. So the first thing to check is if the size is the same. So if these two sizes are different, then they're not equals, no matter what, right? I mean, you can't have it equal. So that just gets you a really fast check. The second, almost as fast check is we're just going to do 1 byte comparison. Check the first character, right? The string's first character is not equal, but yeah, there's no point. And then we're going to finally call the memcomp, which compares byte by byte up to the side. So it compares to see literally these bytes are the same. So it's questionable whether you actually even need this, because in a really fast, something wrong, because if you really optimize, I don't know how, because if you really, in some versions of GC, if you really optimize the memcomp, this actually just inlines it, and it actually just does a really fast assembly loop, so that if the first one's not equal, it'll just break out anyway. So it actually isn't a function call anyways. You don't need to call the function, but who knows? Maybe this is for unoptimized or for whatever. But memcomp is pretty fast. Maybe it's slower. This is, I'll skip this class. Maybe this is slower because these are indirect pointers, so it can't. No, I mean, they're just pointers you love. But anyways, so basically the point of this code is just compares, and then there's a bunch of other stuff that happens for different sorts of comparisons. So the equals equals case is fast, and then less equals, greater than equals, and so forth. This is all basically just using the memory comparison, functions. So I guess memcomp does do a less than or greater than, right? Because it actually doesn't just show you whether they're equal. Right? So actually, if you look up C, so the reason why I'm going into all this detail is because at the end of the day, they're all just implemented in terms of C functions, right? Because the Python interpreter is implemented in C, so we're using standard C library. This is a standard spec for a memcomp with 2 pointers and a size. Yep, it returns all 3. Integer greater than, equal than, less than 0 is greater than, equals, less than pointer object. And I think it's, first pair of bytes that differ in objects being compared. Yeah, so it falls back on the C semantics. So actually the semantics of this is just like the C semantics. Okay, so that's the string equality. There's some other things in string, concatenation. So we won't go through the entire crazy process, but the other thing you can do with strings is you can add them, right? So x equals hello, y equals world, y equals world. X plus y is, it just sticks the strings together. So what happens to x and y? Nothing happens to x and y, right? So concatenation actually just creates a new string. So nothing happens because x and y are immutable. If you go like this, it actually moves x to a new thing. But notice how nothing actually, this is important to illustrate. Okay, so what we have here is x points to some hello object, y points to some world object, and what this x plus y does is it actually creates a new object called hello world, and then it sets x to point to that, right? So nothing actually happened to this hello. Now the reference count went down on it, so if no one else is pointing to it, it'll disappear. But nothing. It's not the case that this hello magically modified this hello world. This does not happen, right? In Java, there's a string buffer class, I think, that does mutations, but strings do not modify. So if I go like this, x is hello world. So we'll spend the next 5 minutes or so just looking into concatenation. So PyString concat, you can imagine once you're already in string.c, you can imagine these two are things to concatenate, and then we're going to call string concat, and then this has a bunch of complicated code that does essentially what you'd expect. It would allocate size, right? It just makes one that's the size of the double of both of them. Negative, there's a lot of checks for a lot of stuff. Malloc right here, this allocates a new object, a new string object. That's, malloc is a way that dynamic allocate memory. There's probably some wrapper around it. And then it memcopies, it just copies. So this is exactly what a string concatenation you think would look like. It allocates a new thing with size for both of them. It copies the first one in and copies the second one in. So this one copies, right? This one copies, it allocates something double as big. It copies the first string into here, then offsets copies the second string into there, and it just cleans up. And it cleans up after itself by putting a 0 byte in the last one, and then it returns the new pi object. So this is what you exactly imagine for string concatenation. So this in itself is not super interesting, but the interesting part is how it actually gets in. So how do we actually do concatenation? In Python, how do we activate the concatenation operator? What was the operator? Do you remember?
Plus operator.
This is a plus sign, right? So if you actually look at the bytecode, what would the bytecode be?
That would be add.
Yeah, it would be an add. Right, it would be a binary add. So it's actually not there's no bytecode for string add, right? There's actually not a bytecode. If you actually, let me write this code. Oh, I almost got it. X plus Y. Here's a binary add, right? That's all the bytecode is, the binary add. Python compiler is not that smart. If I said these two are numbers, this is a binary add. It's the exact same bytecode. So only at runtime can we determine what to do, because at compile time, the compiler is really stupid. Like, actually, imagine if you actually have a better compiler, you can know. I mean, you could do this for your project. You can know that this is not a binary add. You can know this is an integer add, right? It's clearly obvious if you stare at it, it's an integer add. But the Python compiler is really stupid. It just compiles one line at a time. It doesn't care. It just defers all the decisions to runtime, because then you can do stuff like this. I mean, you wouldn't want to do stuff like this. You can do. This is completely legal Python, right? You can do that. And at runtime, something will just blow up, right? It just blow up, right? It just says it's an error. But it doesn't blow up until you run it. It only blows up when you run it. It doesn't blow up when you compile, because it's just a binary add. So this is what we did. This is an exercise not last time. Binary add, they're not integers. Then we actually, they're both strings. So this is actually another fast case. I thought we have to go into a slow case. Where is the slow case? Pi number add is a slow case. So they're actually both strings. So notice how the binary add, the interpreter baked in, it knows that integers are special because you add integers a lot. It also knows the strings are special because you know you add strings a lot. And if they're both exact strings, we're just going to call string concatenate. It's actually very fast. It's extremely fast. So that's the mystery of that. That mystery is solved. It just jumps right into string concatenate. Otherwise, we're going to have to jump into here, and this is the kind of most tricky part about the assignment is figuring out what this thing does and all the hoops it jumps